Let's start today's class. We will talk about applied aerodynamics, flow over airfoil, real case, and then we will talk about influence of flaps and leads, idea how to control lift with external devices, and with this information probably we will finish chapter 4 today. I think our today class will be not very long, so let's start. Next time, if we finish today, we will already talk about wings. Please do not forget to ask your questions in the comments. See, there are no questions for now. Before I forgot, I would like to tell we will have no class tomorrow. Please look my videos about simulation of airfoils, prepare your simulations. And I hope next week we will have a practical class in aerodynamics synchronous. Okay. This case, real flow around airfoil, we see on 3 different examples. First example is so-called thin airfoil, which thickness is relatively small with respect to size of hood. This airfoil here, let's see, is a NACA 4412, standard 4-digit airfoil with 12% thickness, quite typical representative of cambered thin airfoil. Looking to characteristic of this airfoil, let's take a look on figure F. We see that lift coefficient behavior is linear between stall conditions, right? And this line of lift coefficient is also shifted on alpha L0, which is approximately 2 degrees or minus 2 degrees. Okay, maximum value of lift coefficient is a bit more than 1.5 and minimal value is -1 for negative angle of attack. Sorry. Already had today a lot of meetings, a lot of discussions, so not perfect voice. Linear behavior. Now let's take a look on flow patterns for various angles. First, these 4 figures showing to us flow starting from 2 degrees. Angle of attack, figure A, where lift coefficient is relatively small, 0.35. Such small flow inclination is almost invisible on figure A. It looks okay, close to horizontal initial flow direction. Such flow around airfoil is smooth and can be simply calculated by Laplace's equation or simulated in ANSYS fluid. For people who already started simulations, in a visit simulation, you can obtain a very, very similar picture to this one. Then, when we increase angle of attack from 2 to 5 degrees, we observe on figure B higher value of lift coefficient, proportionally higher. We just saw that graph, right? You saw its linear function. Proportionally higher lift coefficient and flow behavior around airfoil is a bit different now because angle of attack is changed, right? Lift coefficient increased results in different distribution of flow pattern. I would like to remind you that flow pattern directly reflects on lift because flow lines or streamlines we see here visualized, they can be directly converted to velocity function and they can be converted after to pressure function and lift coefficient as a function of pressure and pressure coefficient. Okay, so visualization of these lines is not just direction of flow. They have more significant meaning, this xi function. And just reminding you that velocity parameters from xi function is xi, okay, one value, or let me write better, xi1, xi2, etc. So constant values of streamline function. And velocity coefficients can be easily calculated like derivative of this function. dxc by dy is u component of velocity, and the minus dxc by dx is v component of velocity. After we have these two components of velocity, we calculate velocity vector, and by Bernoulli equation, we calculate pressure, pressure coefficient, and lift coefficient CL as a sequence. So once we know the distribution of streamlines, we know everything on this airfoil. How we know that lift coefficient will appear? Just looking on picture of flow. We see if flow is not symmetric on the upper and lower side of picture, it means that pressure distribution is not symmetric as well. And this flow will definitely have lift and corresponding lift coefficient. Let me check one thing here. I think my pen is too thick. Okay, let's see case number C. Case C is corresponding to 10 degrees angle of attack. In such case, we already have significant inclination of flow with respect to airfoil. Angle between chord direction and flow direction. I think for all these pictures, what is changing is this angle inclination. Okay. I will try to make flow direction and airfoil direction. This is our angle of attack. Like this. It's different from simulation because on simulation we incline flow direction. We do not incline the airfoil by itself. All right, it's relatively. It's all equivalent, let's say. Proportionally, we increase angle of attack, and proportionally, we have increased lift coefficient. 1.2 is close to its maximum. And then on figure D, we start having the conditions close to stall conditions, point where there is a large separation of streamline. One other, let me zoom this on. One other property of streamline, that between two streamlines we have constant mass flow rate. We have constant mass flow rate, so it means that here in the biggest section, mass flow rate is same as in the smaller section. Since its flow area is bigger, probably it will mean that we have problem with the velocity, right? Velocity starts to separate. Average velocity is much smaller, and velocity will start to separate. So it's 15 degrees angle of attack and a bit smaller than 15 degrees. Once we will increase just a bit angle of attack, we will see a significant change in flow picture, as you might see on figure E. Here, 15 plus means a bit bigger, a bit higher than this critical angle of attack. We start to have flow separation everywhere on the upper side of airfoil, and we have a drastic decrease of lift coefficient, as you can see on this graphic, this part here. So this point is near 15 degrees. Flow separation happens differently for different airfoils. For some airfoils, like thin airfoils, it might happen with such a rapid transition, right? In figure D, we have almost no flow separation. In figure E, we have huge flow separation the next moment. This is why thin airfoils are not always perfect for control of lift coefficient for high angles of attack. There is a big chance of flow separation. Let's go and see now another example is thick airfoil. NACA 4421. It's also NACA 44 as the previous one, but now we have 21% of chord of this airfoil. Not 12, almost 2 times thicker. What happens in such case? Flow behavior is very similar for case A and case B. Flow patterns are smooth. This such flow can be calculated with Laplace's equation, and lift coefficient can be obtained with Laplace's equation or numerical method we discussed last time, source panel method, to obtain lift and flow distribution. Then at 15 degrees also starts flow separation, as in the previous case, but in this case, flow separation has a small range, small size, okay, and such a small volume of flow separation is typical for thick airfoils. Then already at much higher angle of attack, around 22.5 degrees, we can observe flow separation in a large volume above airfoil. And of course, due to this process, we have a decreased value of lift coefficient, but such flow separation on large volume happens at significantly higher angle of attack. I would like to remind you difference in performance between thin and thick airfoils. Usually thin airfoils, these are better for faster flight. Right? For high velocity, they support higher velocity for flight, but they have a smaller lift to drag ratio. Thick airfoils, they are better for slow velocity, and they have usually bigger lift to drag ratio, so they are more efficient, but they fly slower. Thin airfoil, they are less efficient, they fly faster. Here, I think it's a comparison between flat plate and NACA airfoils, 4412, 4421. They're those two which we saw in previous figures. They have same behavior of lift before 10 degrees, more or less, approximately 10 degrees. Let's make a vertical line. So let's make a vertical line more or less until 10 degrees. They have very, very same behavior. And after flow separation starts, these two airfoils behave in a different way. When thin airfoil has a very sharp change of lift coefficient, sharp drop of lift coefficient, but top maximum is higher. Thick airfoil has more smooth change of lift coefficient, so it can work effectively until more or less 20 degrees, or even a bit more than 20 degrees. I mean, effectively, that still would have, even with the flow separation, good value of lift coefficient. Okay, so range of operation for this thick airfoil is bigger. And we compare these two airfoils, good airfoils. They are not the best airfoils, but they are good airfoils from performance point of view. We compare with just flat plate, just a plate. we consider flat plate as thin airfoil. The thickness is very small with respect to size of this plate. And using theory of thin airfoil, we can predict lift coefficient. Just a moment, we have a question. Let me see. Will CL get the maximum value when the fluid starts to lift off the airfoil? Not always. You mean lift off is separate, right? Separate is the same word. When flow starts to separate from airfoil does not mean that we already obtain the maximum value of lift coefficient. It's more complex. I saw airfoils which have, even at small angle of attack, at zero angle of attack. Let's have this as an example. Let's assume it's not 4412, but another airfoil. I saw airfoil that even at small angle of attack already has small zone of flow separation. It was proven not just numerically, but it was proven also experimentally. Such flow separation exists on some small vortex on the end part of airfoil. And with increase of angle of attack from one small angle to bigger angle, we have increase of flow separation. Then for bigger angle, more increase of flow separation. And with this change of angle of attack, growing vortex. We have growing vortex, but same time we have growing lift coefficient. I saw such an example. So we cannot say that only when flow separation appears, flow starts to suffer and lift coefficient starts to drop. No, I think lift coefficient starts to become nonlinear. So it becomes a curvature in lift coefficient, somewhere where we observe presence of flow separation. Okay, but it will not start to decrease. I think the slope of lift or inclination of this curve, which is called lift slope, how we can define it's CL. Oh, let's see. That's right here. DCL by D alpha, something like this. This lift slope will start to decrease. But the value of lift will continue to increase until some certain point, until the point where will not compensate any more change of angle with the distribution of pressure. Because what is lift coefficient for us is mostly composed by pressure distribution and a little by shear stress distribution. So until the moment we can rise pressure difference, we have increase of lift coefficient. At the moment where we cannot rise pressure difference anymore, for example, at the moment when this vortex becomes too big, our pressure will not grow anymore. The pressure difference will not grow anymore. We will not have increase of lift coefficient anymore. So I think that lift coefficient growth is related not with existence of flow separation, but with the size or relative size of flow separation, how much flow separation occupies of total size of airfoil. Relation between area of flow separation and the total area of airfoil. Okay, I think it was clear. Let's return back, okay, to this question. And we see flat plate. Flat plate is very bad as airfoil. It will have extremely small lift coefficient. It will have lift coefficient due to pressure difference, but it will be small, and flow separation, some significant value of flow separation starts already at very small angles of attack. So this curvature, as I just told you, is representing flow separation or start of curvature. We can have this example right here. Oh, you see, I put this vertical line somewhere between 0 and 10, so maybe it was 5, 6, 7, somewhere here. And on the next picture, we already see that the flow separation happens already at 7 degrees. But I think it also happens before 7 degrees. So what we have at a small angle of attack, like 3 degrees, lift coefficient is extremely small. But the problem at this point is this leading edge. You already see that it lifts flow. So it creates local vacuum at the volume on the top of a plate. And this local vacuum, it will destroy all flow structure because it's a very sharp change of pressure. And then you can see on 7 degrees angle of attack already is destroyed flow. It started flow separation because this edge here on the front is sharp. Subsonic aerodynamics, and especially incompressible aerodynamics, does not like sharp edges. Everywhere where sharp edges happen in front of flow, it will start to create a vortex associated with this sharp behavior. So flow will start to become smooth. This is why creating a bubble around this sharp edge. And this bubble is having significant volume. Inside this bubble, we assume that velocity would be similar to 0 or close to 0. And because velocity is small, pressure in this bubble will be similar to pressure on the other side of the airfoil, or will be close to stagnation pressure. So this part of pressure will not participate in creation of lift, since pressure on the top and on the bottom in this zone would be similar. Here pressure is a bit higher. On the lower side, pressure is a bit higher, but in general, pressure difference is not big, it's very small. And what is contributing to creation of lift here in this case is upper and lower zone, which I marked by blue color. So only this part of plate, very insignificant, small part of plate, let's say half. And then for higher angle of attack, we see complete flow separation. So here in this region with the 9 degrees angle of attack, we can assume that flow separation happens everywhere. This picture does not show us vortex formed by separated flow, but we assume that flow is separated since mass flow rate or distance between streamlines is equal to mass flow rate or volumetric flow rate, since distance here on the leading edge, right here, on the leading edge of plate is 0 or close to 0, we can say that quantity of mass going here at this region would be also very small. So it means that flow is only recirculating inside this zone. Flow is not, say, flowing in one direction, it's just rotating. Flow is turbulent at high angles of attack, like 15 degrees is totally developed flow separation, and the flow separation size is extremely high. Maximum lift coefficient for these two cases, you can see here 0.7. For 15 degrees, for 9 degrees, 0.75, and for 7 degrees, 0.7. So once we increase angle of attack from 7 to 15 degrees, we see no difference in performance. So it's absolutely useless to use flat plate for higher angle of attack than 7 degrees. And as I told you before, according to theory of aerodynamics and also compressible gas dynamics, you will see that even a wedge or small conical body would be much more performant in terms of lift creation than plate. Nobody uses plate in aerodynamics. For creation lift, for creation drag, yes, as we discussed last time, to creation flow recirculation, plate is extremely efficient. It allows to decelerate airplane and has light weight. Here on this picture is the effect of airfoil thickness on maximum lift coefficient. This is typical for some specific airfoil, 63-200 series airfoils for different Reynolds number or different flight velocities, let's say, if we assume air. And we see that for many flight velocities, there is an optimal value of maximum lift coefficient. Okay, this one close to 12 degrees for an airfoil can be used this thickness as a good value, or let's say, I don't like so much this word good value, because how much is good, everyone decides. It's very subjective definition. But if we see from point of view of lift coefficient, we see that for most cases, 12 degrees, 12% of thickness of airfoil is good. We see that maximum of lift coefficient changes for different Reynolds number. With the increase of Reynolds number, we have increase of lift coefficient, but is for this airfoil. We cannot say if same behavior will be for all possible geometries, right? But for this particular airfoil, with increase of Reynolds number, we have increase in the maximum lift coefficient. Also, if we compare, analyze this picture and compare different airfoils, we will see that 12% is not so much better than, for example, 15% airfoil or even 70% thickness airfoil. They can be used as well if you need a high value of lift coefficient. What could be advantages of thicker airfoils? As I told you, they will be more efficient for low velocity flight, and they will be also more stronger from structural point of view. Thin airfoil, I need to, I think need more attention from structural point of view because of material properties. Next question we discuss is influence of flaps or flap deflection. What are the flaps? Flaps are some devices at the end of the wing which incline and change overall lift coefficient on airfoil. Flap can be inclined in positive or negative direction, and this is the way how all modern airplanes control their lift, their flight. From simulation point of view, it is possible to provide, right? And we can observe then for same angle of attack, alpha 0 for both cases would be difference in flow picture once we change flap inclination from 0 to 15 degrees, totally different flow behavior. If we look to lift to angle of attack plot, we will see that for positive inclination of flap, we gain positive effect on lift coefficient, can be in order of 0.5 plus 0.5 lift coefficient, but it also depends on size flap. It's not a definitive value. And for negative also, since it's symmetric or mostly symmetric structure of flap, we have same but negative gain on lift coefficient. So once takeoff is realized, we need more lift. Our angle of flap inclination will be positive, creating some additional lift, so we can take off at smaller velocity. Then during the flight, flap angle is close to 0. So we have sustained high efficiency flight at high velocity. And then when descend, there are several ways, of course, controlled by motor, controlled by flap, but also having negative flap inclination, we decrease overall lift coefficient and we can descend this airplane. There are other technical solutions on flight control. They are called slats, leading edge slats, leading edge drop, Kruger flap, and other technical solutions you can find in the literature. They are controlling the leading edge flow behavior. And with such devices, we can also change our lift coefficient. We need to remember that changing lift coefficient will also change drag coefficient. So it should be supported, this change of drag coefficient, by power of engine. It should be also controlled during flight or maneuver. LED, unactivated and activated, extend possible angle of attack and extend the maximum of lift coefficient. For example, here for some airfoil which is unknown, we can observe that with any of these devices used, we have, I think it's for NACA 4412. We have approximately 0.5 or 0.7 lift coefficient extra. Let's see how flow picture is developed. Here at 10 degrees angle of attack, this LED is at some position. Position of LED is very important. How is the angle? What is the distance? Main purpose of this LED is to organize flow in such a way that flow separation will be avoided. So we need to design and control this LED in such a way that flow separation will not happen. For example, look at the angle of attack 25 degrees. This LED is in such a relation, in such distance and inclination to main airfoil that it organizes flow in such a way, avoiding flow separation at 25 degrees. I would like to remind you that we already had flow separation for this airfoil at 15 degrees. So without LED, we can work until 15 degrees. With LED, we can work until 25 degrees and can gain additional lift. Then near 30 degrees, of course, we will have flow separation. It's inevitable. Close to 30 degrees starts this process of flow separation, and at angles more higher than 30 degrees, we can observe a big region where flow separation will occur. Okay, by any means, it's not possible to avoid such process, but with the LED, with another technical devices, we can extend range of operation of airfoil. Main purpose of this device is not to create additional lift, but to extend limits of angle of attack, and main airfoil would gain additional lift during its inclination. Okay, more complex configuration can be seen here. airfoil with leading edge and trailing edge high lift mechanisms. Trailing edge device is a multi-elemental flap. It's extremely complex from technical point of view, from mechanical point of view device, which allows to us different configurations of operation. There is a cruise configuration when wing has completely it repeats original airfoil, high-efficient airfoil or high-efficient wing. Then at takeoff configuration, it deploys elements in such a way that perform highest possible lift coefficient with the increase of area, with increase of size, and with organizing flow pattern in such a way that flow separation would be prevented on the top of this wing. And the third one is the landing configuration, which is also organizing to us high lift, but also organizes high drag to decelerate. So we must decelerate and land. So two configurations. Why high lift? Because we would like to land at the slowest possible velocity to have shortest possible landing size or landing lane, and so we need the small drag for deceleration as fast as possible. At this moment here, we can see an example of such perfect, from technical point of view, operation of the wing. It's a cross section of the wing and various flaps, and one LED at the front part. So this LED at front part organizes flow in such a way that with all other flaps, it's kept without flow separation. In such a way, no flow separation means we have very high pressure difference. Since size of this object is big, we have a big area and a big force. And since part of these elements are directed normally to main flow, this device creates extremely high drag, pressure drag. So from all points of view, it's perfect. From technical point of view, it's very complex. Please, when you take an airplane next time, take a look how this wing on real airplane works. It's very, very interesting to observe. Oh, there are many videos on the internet for people who had no, who will not have flight. In the near future, you could see videos and see how wing works. It's extremely, extremely interesting. Here I had a video about flow with LEDs, but since it's just a presentation I'm showing you, you will not see it as a video. But this video is available on YouTube, and I recommend you to make a simple search on Google and find something like experimental testing or test of airfoil in a wind tunnel. This video is made maybe 60, 70 years ago. A classical one. They change angle of attack, they change flap inclination, and in this test they visualize streamlines. You can see here streamlines visualized by smoke. These are smoke lines, smoke flows from small pipes probably. And behind the airfoil, you can observe flow separation region and turbulence. Very nice videos. I recommend you to make a simple search and assist such videos. I hope in near future I will, if you do not find, I can show you and we can discuss together such process or such tests, since we do not have yet in Gamma. So that's it about chapter 4. I would like to finish today. Please let me know if you have questions. Our today lecture was short, as I told you before, because we had not so much material. Next time I will start talking about chapter 5, incompressible flow over finite wings, and I think soon we can finish aerodynamics. Soon it means in 1-2 weeks, in 2 weeks probably, we can finish lectures on aerodynamics, and then all the rest of time we can spend on discussion, your questions, talking about problems in simulation, in calculation, preparing for final reports, right? I hope that's fine for you. Please do not forget to ask questions. I can wait 1-2 minutes if some question appear, and meanwhile I will take a glass of water.
Professor, I have a question related to the thickness of the airfoil that you presented earlier. Related to the airfoil's thickness, I would like to know about the mitigation, the actual mitigation that the cambering of the airfoil's geometry will have to make a reduction on the effect on the lift coefficient in thin airfoils, because I see that there are a lot of thin airfoils in which the geometry is not mainly aligned. The airfoil is mainly cambered upwards. So does this have a possible a positive effect on thin airfoils, and how much is this actually relevant?
Let me try to find cambered airfoil on all these slides. Okay, any of these which are not symmetric are cambered. I would like to find one which is better. Okay, maybe this one, 2412, classical one. So please let me understand your question. I could not understand your question. You do not like cambered airfoil because they are not symmetric, or what?
No,
What's the
no,
problem?
no, not at all. I might have used the wrong term. With the central line of the airfoil is dislocated upwards.
Yeah.
Like with 6409, I think the airfoil that I'm analyzing. So it is a thin airfoil, but it is not a case like a flat plate, because mainly the geometry is going first upwards and then it's going back down. So mainly it's so much cambered that the most of the geometry is above the chord line. So it is a thin airfoil, but the upward surface of the airfoil is more like other thick airfoils. So how much is this actually positive to the thin airfoil?
Very interesting question. I never thought in such a way that could be positive. Camber line curvature could be positive for thin airfoil. There are different airfoils for different applications. There are airfoils which are extremely curved camber line, which have extremely curved camber line. For example, airfoils used in turbo machinery, because the main objective is to keep energy, to transform energy and to also rotate flow direction, or to, let's say, rotate flow direction on some certain angle. This is why camber line can be really displaced, or with respect to a chord line, for example, something like, let me try something like this, right? You say about some geometry similar to this.
Yeah, exactly.
So so there are several purposes, right? In such airfoil can be not just receiving of efficiency, but also rotation of flow for next utilization. Like in turbo machine unit, we have special regime of transonic flow or even supersonic flow. So flow goes from subsonic to supersonic regime, and it requires specific rotation to obtain maximum efficiency. I cannot say it's as an advantage or disadvantage. It's just a process which goes in such way. So flow must be organized in a such way that reduces the losses. I think we must think in from aerodynamic point of view always about efficiency. How efficient is this or another transformation? What should we expect, not from point of view, not only from point of view of lift and drag, but also maybe there are specific restrictions on flow direction after. Something like this. But I think it's a very interesting question about the relation between thickness and curvature of a camber line. Highly cambered airfoils, I'm even not sure can be simply described by thin airfoil theory. Because thin airfoil theory, as Anderson says to us, can be applied only to airfoils where velocity of perturbation or change of velocity between inlet and outlet is relatively small with respect to infinite velocity. In the case of such airfoil you are asking, I think we have a significant change of velocity in X and Y direction because velocity is rotated. So in this case, I'm not sure we can use, but probably we can until some limit, but not in all cases we can use thin airfoil theory and prediction by this theory. It would be nice to understand this question in future, relation between thickness and camber line. Do not forget that curvature of a camber line is strictly related to alpha L0. Bigger is this curvature, bigger is this alpha L0. So at even small or zero angle of attack, you obtain a huge value of lift. So probably is this thin airfoil working at transonic conditions because it works much better at transonic condition than thick airfoil. So small thickness must be used for high velocity applications, and the high camber, especially to use this airfoil in a very low angle of attack, receiving high value of lift or lift coefficient. Probably this is the purpose, but we can talk about, we can see. If you will be still interested in this question for our next meeting, I can read some book. I have several books about such shape of airfoils, and we can continue this discussion on our next meetings, if you would be interested to discover more about it.
Yeah, that would be great, Professor. Thank you.
Okay, you are welcome. More questions, please. Okay, people, thank you for your participation today. We will finish. We continue on Tuesday, probably, I hope. And as I told you, on Tuesday we start chapter 5 from the book. Please watch videos tomorrow. Do not miss this moment for studying simulation, CFD. It would be important for your work 2 and work 3. And next time I'm expecting more questions. Have a nice weekend and see you next week.
Goodbye, Professor. Nice weekend.
See you.
Bye.